Now let us see the hydrolysis of cyanide catalyzed by alkali or acids. Now consider cyanide group. The carbon is having slight positive character and nitrogen having slight negative character because nitrogen is more electronegative. Now consider the hydrolysis of cyanide by an alkali. You take one NaOH molecule, then the OH negative is taken from NaOH and OH negative attacks this carbon of cyanide. One lone pair of oxygen has now 3 lone pairs. One lone pair of oxygen is donated to carbon, and simultaneously the CN pi bond will be rotating through an angle of 180 degree and reaches the H atom of an H2O molecule, and there HOH ionizes as H positive and OH negative, and this OH negative is given to Na positive so that NaOH is created back. Now this H positive unites with N to get NH bonds. Now here oxygen unites with carbon, and when oxygen unites with the carbon, one electron of oxygen is given to carbon so that its negative charge is neutralized. When this bond moves in this direction, the share of this carbon is also moving in this direction so that carbon loses one electron, and when this lone pair is given to this carbon, one electron is gained by carbon so that the charge over carbon is also neutralized, and then it is gained back, so that the net reaction is addition of NH and OH. So chemical reaction with water occurs here. It is an indirect reaction. Water is not directly reacting, but indirectly it is addition of H and OH. So water splits into H and OH and adds to the cyanide, so that the reaction is called hydrolysis. So hydrolysis is chemical reaction with water. Water splits into H and OH and adds to the structure. Now the product formed is C double bond NH-OH. Now this is a resonance hybrid where the lone pair of oxygen goes in between carbon and oxygen, and this pi bond here moves over nitrogen. In the sense, this pi bond is formed by the overlap of the orbital of carbon and the orbital of nitrogen. And when this arrow is shown over nitrogen, the orbital of nitrogen takes the entire electron pair and forms a lone pair here. And since during that process the share of electron of carbon is gained by nitrogen, there is a negative charge. And when this pair of electron moves in between this carbon and oxygen, initially carbon has a positive charge. When this pair of electron, that is lone pair, moves in between these two atoms, one electron is gained by this carbon so that the charge over carbon is neutralized, and we create a positive charge over oxygen. So that is a resonance hybrid. So there is a tendency for formation of C double bond O from this structure. Now there is a double bond, and the suffix used for naming double bond is ENE, EN. And again this structure contains an alcoholic group. So ene plus ol, the ol is the suffix of alcohol. We get enol. So that this is an enol. Now enol has a tendency to undergo resonance like this, and then the tendency for a CO bond to become a double bond, and the CO bond becoming a double bond with oxygen positive will be strongly pulling this electron in the OH bond towards itself. So there is a tendency for removal of H as H positive, and since there is a negative charge over nitrogen, this H positive can combine with nitrogen, and that happens. That is the extreme case of resonance, so that this bond will be moving in this direction. You think mechanically, this bond moving in this direction to an angle of say 90 degree, and simultaneously this bond will be moving through an angle of 90 degree in between N and H. So we get C double bond O, NH plus H giving NS2, and this is the keto form, and this phenomenon is called keto-enol tautomerism. In tautomerism, there is positional change of atoms. The position of atom is changed. Now originally the position of hydrogen was in combination with the oxygen. Now it changes its position to the position where nitrogen is now connected to hydrogen. So hydrogen changes its position from oxygen to nitrogen, and this phenomenon called keto-enol tautomerism, and the product here is called an amide. An amide is having the group CONS2. Now hydrolysis will not stop there. The amide formed has also resonance structures like this. The lone pair moving in this direction, C double bond moving in this direction, we get C double bond NH2 positive and O negative. So that the oxygen atom has a partial negative charge in the resonance hybrid. Now we consider the amide structure, then consider another molecule of NaOH. Now there is a tendency for CO bond to polarize or ionize in this direction, so that carbon gets positive charge, and OH negative with its pair of electron establishes a bond with this carbon with the simultaneous movement of this electron pair over oxygen. We get O negative and OH connected to this carbon. Now the negative charge is over oxygen atom, because this pair of electron is completely shifting into the orbital of oxygen, so that the share of this carbon is obtained by this oxygen, so it gets an extra electron and a negative charge. Now carbon should get a positive charge, but when lone pair of oxygen is donated to this carbon, one electron is gained by this carbon, and so the charge over carbon is neutralized, and again when one electron is lost by oxygen, its negative charge is also lost, so we get CO negative and OH. Now then this structure being unstable due to these groups possessing lone pairs, will try to remove a group which is somewhat bulkier is NS2 group. So NS2 group is removed, and for this the lone pair of oxygen atom establishes a bond with the carbon and carbon, and so a pi bond is formed between carbon and oxygen, means a pair of electron now becomes a bond pair. Then the valency of carbon increases, and then this bond will be rotating through say an angle of 180 degree. So this bond rotates like this and reaches a hydrogen atom of water molecule. Now the water molecule ionizes as OH negative, so H positive connects to N of NH2, and this OH negative is given back to Na positive, so NaOH is a catalyst. Again the reaction involves the removal of a molecule of ammonia, because NS2 combines with the H positive producing NS3, and this becomes C double bond O and OH. So we get COOH, that is carboxylic acid. So in reaction with the sodium hydroxide, a cyanide or again an amide can liberate ammonia gas. So ammonia gas has got a pungent smell, peculiar smell. So this is a test for an amide or cyanide, because during alkaline hydrolysis, if the hydrolyzing agent is acid, ammonia will react with the acid producing the ammonium salt, which has no smell. If the reaction is conducted in alkaline medium, then there is liberation of ammonia and smell of ammonia. So if an amide or cyanide is hydrolyzed using alkali, sodium hydroxide, smell of ammonia indicates that it can be a cyanide or amide. Now coming to acid catalyzed hydrolysis, we take HCl as the acid. Now there is a polarity of nitrogen as delta negative. So one H positive from an HCl molecule is taken by nitrogen. This bond, CN bond, rotating through an angle of 180 degree and reaches H positive, so that the share of carbon is obtained by H positive and it charge neutralizes and we get an NH bond. This triple bond becomes a double bond. Now carbon gets a positive charge and a molecule of water donates its lone pair towards this carbon, and one electron is given to this carbon, so that its charge, positive charge, is getting neutralized, and then oxygen atom gains a positive charge because one of its electrons is given to carbon. To neutralize the positive charge over oxygen atom, this OH bond is completely taken up by the orbital of oxygen, so we get a lone pair here, and H positive is released, so that this H positive combines with the Cl negative to get back HCl. So that the reaction is addition of an H and OH, so it is hydrolysis, and HCl is a catalyst. So all these reactions occur simultaneously, that is reaction with H positive and reaction with the H2O and removal of H as H positive. So net reaction is addition of H and OH. So water splits into H and OH and adds to the structure. So it is a hydrolysis reaction, that is chemical reaction with the water catalyzed by HCl. Now we get an enol as the product, and enol. Now enol can tautomerize to this OH bond going in this direction, this OH C double bond NH pi bond going in this direction in between N and H, so that we get CONS2, that is amide. Then consider another HCl molecule which donates H positive. Now this CO bond, C double bond O, has a tendency to ionize as C positive O negative, so that this oxygen combines with the H positive by shift of this bond in between O and H. Carbon gets a positive charge, a molecule of water donates its lone pair to H positive carbon, so that one electron is given to carbon. So we get positive charge over oxygen atom. Then this OH bond will be shifting over oxygen atom to neutralize its positive charge, so H is removed as H positive, so that the H positive taken from this HCl molecule is given back and we get HCl back, so HCl is a catalyst. And the net reaction is addition of an OH, an OH and the H, that is water. So water reacts chemically, it splits into H and OH and then adds to the structure. Now these groups OH, NS2 and OH, both all these groups possess electron pairs, and this group is somewhat bulkier because it has two hydrogen atoms. So the system will try to remove this NS2 group, and for that the OH bond will be shifting in this direction and NS2 will be shifting in this direction. So this bond shifts in between H and N, this bond shifts in between C and O. We get COOH and NS3, but here the thing is that NH3 will be reacting with the HCl producing NH4Cl. So if acid is the catalyst used for hydrolysis of a cyanide or an amide, you won't get the smell of ammonia. Now coming to some more conversion reactions, that is isopropyl alcohol to iodoform. Isopropyl alcohol is CH3CH, CH3OH. Now CH bond here breaks, a valence is created over this carbon and a valency over this hydrogen. Then OH bond breaks, valency over oxygen and valency over hydrogen. The valency over carbon combines with the valency over oxygen to produce C double bond O. Now these two hydrogen atoms combine with the valencies over iodine atoms to produce 2Hi, and this molecule CH3COCH3 is called acetone. It belongs to the family of ketones, and this reaction is an oxidation reaction because removal of hydrogen is oxidation. So hydrogen is removed from the structure. Now the product is called acetone. Then acetone can be further reacted with iodine. Now it is not oxidation reaction, but it is a substitution reaction. There are 3 CH bonds in the methyl group. The CH bonds break, producing valencies over hydrogen atoms. 3 iodine molecules react. The valency over iodine combines with the valency over H. This hydrogen with its valency combines with one more iodine. This hydrogen with its valency combines with the third iodine. Now the remaining valencies over carbon will combine with the valencies of iodine to produce Ci3 group. It is called a triiodoacetone plus 3Ha, of course. Now the triiodoacetone will react with NaOH. NaOH is written as NaO bond H. Now you put a box inside which contains Ci3 and H, so that C will combine with the valency over H. The valency over C here will combine with the valency over H. So we get CH bonds, then CHI3. It's an yellow precipitate called iodoform. Then CH3C, this valency will combine with the valency over oxygen atom. So CO bond will be formed. CH3C double bond ONA. CH3C double bond ONA, that is sodium acetate. Now here, one factor which favors the substitution reaction is that CH3C double bond O. This CH bond can shift in this direction and this one. So it is a type of hyperconjugation, so that the hydrogen atom has a polar character due to the presence of adjacent ketonic group here, so that these hydrogen atoms may be easily replaced by iodine atoms. So that it's a preparation of iodoform from isopropyl alcohol. Now next reaction is conversion of chlorobenzene to para-nitrophenol. Now chlorobenzene cannot undergo nucleophilic reaction because the CCl bond is strengthened by resonance, partial double bond character. Now again there is pi electron density in the ring, which will repel an entering nucleophile with its negative charge or pair of electron, lone pair of electrons. So a group which can show greater minus I and minus M effect is used to withdraw the electron density from the ring. This process of withdrawing electron density from the ring is called deactivation of the ring. See, nitro group in para position or ortho position can deactivate the ring. What is done is chlorobenzene is nitrated first using concentrated HNO3 and concentrated H2SO4. We get para-nitrochlorobenzene nitrochlorobenzene and para-nitrochlorobenzene. This nitro group exerts its minus M effect and minus I effect. Now this minus M effect can produce a positive charge at the alpha carbon, so that NaOH is the reagent. OH minus attacks this alpha carbon and the leaving group is chlorine, so OH minus connects and NaCl is removed from the structure. Cl is removed from the structure as NaCl. Now we get phenol, but this is acidic, will react with the sodium hydroxide in the medium, producing the salt O minus Na positive, which can react further with the acid. So a second step is written H positive. Then we get HCl as the acid, OH free phenol. So that is a second step during the reaction process. So chlorobenzene, first nitration, then para-nitrochlorobenzene, then sodium hydroxide, hydroxide being nucleophile. It's a nucleophilic substitution reaction, chlorine being the leaving group, and the temperature here used is 440 Kelvin, and we get the sodium salt of phenol, which is acidic, and on acidification, that is addition of HCl, we get free phenol. Now next conversion, 2-bromopropane to 1-bromopropane. Now 2-bromopropane is shown here, bromine connected to second carbon, 1-bromopropane. Now this conversion is very easy. When you use alcoholic AOH, beta elimination reaction occurs. There are two beta positions which are identical. So H and Br may be eliminated from here, or H and Br may be eliminated from here. We get same molecule, that is propene. Now propene can add on HBr in presence of peroxide, that is called the Karash effect, and the role of it is anti-Markovnich's role, or Markovnich's role is disobeyed, so that bromine, the negative part, goes to the carbon, connects to the unsaturated carbon containing the largest number of H atoms, so CH2Br, and H goes to this carbon, so CH2. Then chloroethane to butane. So chloroethane is also called ethyl chloride, contain only 2 carbon atoms, whereas butane contains 4 carbon atoms. So to double the number of carbon atoms, the reaction used is Wurtz reaction. So you take ethyl chloride, 2 molecules, and 2 Na, removal of NaCl, CH3, CH2, CH2, CH3, that is butane is formed. Reaction is conducted in ether medium, so that is Wurtz reaction. Now benzene to diphenyl, a similar reaction can be used, and that reaction is known as Fittig reaction. And benzene is first converted to the chloro derivative using chlorine and a catalyst, and this catalyst is called halogen carrier. Now ferrichloride is the halogen carrier or catalyst. FeCl3 reacts with Cl2, producing FeCl4 negative and Cl positive, and Cl positive is the electrophile. There is mechanism for electrophilic substitution. We get chlorobenzene, and 2 molecules of chlorobenzene react with 2 sodium in dry ether. 2 NaCl is removed, we get diphenyl. Now then next conversion, tertiary butyl bromide to isobutyl bromide. This is tertiary butyl bromide because this carbon is directly bonded to 3 other carbons. So this is a tertiary carbon and tertiary butyl bromide. Now this group is isopropyl group. Then connect one CH2 to isopropyl group, we get isobutyl group, bromine connected to it, it is isobutyl bromide, CH3, CH3, CH2Br. Now the reaction there is the reaction of this tertiary butyl bromide with alcoholic AOH. All methyl groups are similar or are identically placed, so that any CH3 group can donate H. So all these beta carbons are identical, we say. This is alpha carbon connected to halogen. So removal of H can occur from any of the mediate groups. Removal of HBr here, formation of double bond here. So we get isobutene. Then HBr in presence of the peroxide, we get isobutyl bromide. Now coming to another conversion, that is aniline to phenyl isocyanide. Aniline is a primary aromatic amine and isocyanide group is NC group. So nitrogen is directly connected to the benzene ring. Now this reaction is effected by treating with the alcoholic KOH and chloroform. So this is a reaction which can be used as a test for any primary amine, whether aliphatic or aromatic, because isocyanides are a group of compounds having a very foul smell. So with the smell we can identify the peculiar smell, we can identify the compounds. And when we take the example of aniline, there is an NS2 group and there are two H atoms in the NS2 group. There is one H in CHCl3. The two H atoms here and the H atom in CHCl3 combine to form three H atoms, and there are three Cl atoms in CHCl3. So all they combine to form 3 HCl, and the remaining atoms are N and C, so NC. So isocyanide is formed. Any aromatic primary amine can give this reaction. Any aliphatic primary amine can give this reaction, and all isocyanides are foul smelling gases. So it is a test for primary amine, and again we can use it as a test for chloroform. If a suspected liquid is chloroform, then you take few drops of the liquid and add it to a primary amine, add alcoholic KOH and heat, then we get a foul smelling gas. If you get a foul smelling gas, then we can say that the given compound is chloroform. So this reaction is used both as a test for primary amine as well as chloroform. That is enough. Thank you.